Okay, this is video 21 maybe, I think. And we're already well into tolerances of orientation. We've dealt with the different types of tolerance zones that you might encounter. We've talked about controlling surface elements versus derived median elements, very similar to form. And also very similar to form, we are now going to head into the case where the tolerance zone, or the size of the tolerance zone, can be adjusted based on the material condition of a feature. And I talked to somebody here the other day, and they were going along pretty well until we ran into this aspect, and I can understand why, because of all the stuff packed into that feature control frame, the material condition modifier certainly has a huge impact, and there's a lot of moving parts to it. You have to evaluate it very carefully in order to really determine what the size of your tolerance zone is. Now, I think somebody asked me, why would you use a material condition modifier? When do you use it? There's a million reasons for this. This is something that engineers have to think about all the time, but there are scenarios where depending on the size of a feature, you can allow some control to be larger, the tolerance zone on some control. So if you have large clearance holes in an assembly, the holes that they're supposed to mate up with can be a little bit more out of position. That's a common scenario when you're running a bolt through a clearance hole. But each one of those cases has to be evaluated by the engineer, thought through very carefully, and he has to look at how bad can it really get depending on the worst case scenario. You don't have to do that. That'll all be figured out. It'll be on the feature control frame. You just have to determine what the size of the tolerance zone is that you're going to be allowed, and that's takes a little bit of calculation and a little bit of thought. So what I'm going to do is step back here on these next couple videos. We're going to talk about material conditions and how they relate to tolerances and to limits. We'll talk about the symbols. We've already talked a little bit about the three symbols that are available to us, or were available to us, now only two. And in the second video then, we'll talk about, once we've figured out what the limits are and what material condition we're dealing with, we'll kind of slow step through how to evaluate the tolerance zone based on that material condition for that specific feature. So again, it's a multi-step process, and you have to get the first steps right, or the next steps aren't going to be right at all. All right, so let's start way back, early part of the class, or actually back in blueprint reading back in the fall, when we talked about all the different ways that tolerances and dimensions can be expressed. We talked about bilateral forms, we talked about limit forms, unilateral forms, and we can convert back and forth from one to the other with fairly easily, without making too many mistakes, hopefully. So the idea of material condition actually is tied directly to the limits. So we're going to be dealing largely with the limit form. Now what I've drawn here is two different parts. I've drawn a shaft that is 1 inch in diameter, plus or minus 10 thousandths. I've also drawn a bore that is 1 inch, plus or minus 10 thousandths in diameter. And we're going to talk about the nature of those two different parts, and how we work from the nature of the feature to its limits, and then to its material condition. Now, the reason I picked these two is that they are the two different, let's call them genders of parts that are there. There are male parts and there are female parts, and we all understand that. I want to make it clear that if this were a design, this shaft would not reliably fit into this hole. We'd always have a potential for an interference. So these aren't really designed to go one into the other. They're just the simplest male and female parts that I could come up with. So that's what we're going to deal with. So obviously the shaft we're going to consider a male part, and the bore of course is a female. And what we're going to do is take a look at the limits on each one of these. Now of course, since they're the same dimension and the same tolerance, they're going to have the same limits. 1 inch 10 thousandths and 990 thousandths, 1 inch 10 thousandths and 990 thousandths. Now we have to say, what is the gender of the part we're dealing with? We're going to deal with this one first. It's the male part. And we're going to ask ourselves, which one of those two limits is going to give us the most material? Well, it's obvious, I think, that when that shaft is at 1 inch and 10 thousandths, it is as big as it can be. It's going to weigh the most. So that is its maximum material condition, and we're going to note that here. Moving down to the female part then, we'll ask the same question. Well, this is a female part, and the feature is a 1 inch plus or minus 10 thousandths bore. Which of those two limits is going to result in the most material on that part, or in that feature? The most material, since this feature is taking material away, the most material that's going to remain in the part is going to be when the bore is at 990 thousandths. So we make that a maximum material condition at 990 thousandths for the female part, 1 inch and 10 thousandths for the male part. The rest of it's pretty easy. Once we get those two right, we can't go far wrong here now. So if this is the maximum material condition limit, this is necessarily the least material condition limit. And likewise, this is the least material condition limit. Now this is something that you must do. You must figure out the gender, figure out the limits, figure out the material condition for each one of those limits, and write them down. If you try to keep that straight in your head, you're going to get tripped up every time. So when engineers do this, we do basically this, and we don't always draw the part, but we write down the limits and put the material condition modifier by the appropriate limit. Okay, let's talk about those modifiers. The maximum material condition means exactly that. It means that at what limit is that feature going to have the most material? When is it going to be the heaviest? Here the shaft will be the heaviest at 1 inch 10 thousandths. Here, this part, this tube, will be heaviest at 990 thousandths. Now when you're designing, you know, as let's say an aerospace engineer, he's worried about weight. He's going to be mindful that he doesn't want his features at maximum material condition as very much. He always wants to skew towards the least material condition. He wants to take as much material out as he can because it all adds up. Okay, so maximum material condition is the most material in the part. It has nothing to do with the condition of the material as you would normally understand it, you know, shiny, smooth, hot, cold, nothing like that. It is just how much material is in play here. Now, you know, in any given part, the actual diameter, this could be at the maximum material condition, the next part could be at least material condition, next part after that could be somewhere in between. Okay, each individual part, each individual diameter that you measure is going to be somewhere within that range. If it's not within that range, it's a rejectable part. It's not within the tolerance band. Okay. Similarly, the least material condition represents the limit where there's the least amount of material in the feature. So if we turn the shaft down to the smallest it can be, that will be the least amount of material, and we'll give it the least material condition modifier. I will say this about this S, okay? This S has been around in GD&T for quite a long time. They just got rid of it 10 or 15 years ago. And it stands for regardless of feature size. And what that means is that your tolerance zone, no matter what limit you're at or wherever you are in that tolerance band, it doesn't change. So that is the equivalent of not putting one of these two in the feature control frame. So some wise person realized that we really don't need that symbol. If we don't put it there, that means that you don't get any modification. So only in old drawings are you going to see that. So really all you have to concern yourself with is the maximum material condition and the least material condition modifier. Now, if you look at the symbol table that I gave you, several weeks ago, there were a bunch of letters in a circle. There was a T, and there was a P, and those have nothing to do with material condition. I want you to make sure that that's clear. They look exactly the same, but they're not all material condition modifiers. These are the only two that have anything to do with the material condition or adjusting the tolerance zone. Okay, so in order to really start out on the right foot, you've got to make sure that you are clear on how to convert any dimensional expression into limit form. You have to determine whether the feature is male or female, and once you've established those limits, you can determine based on the gender of the part which one is maximum material and which one is least material condition. Then, once you've got all that sorted out and you've got a piece of paper that looks like this, you're ready to go to your feature control frame and start making sense of the tolerance zone. On the next video, that's exactly what we're going to do.